So our last speaker of this session is our organizer, Berthold Jaeck. He's going to talk about the observation of the backstabbing induced by magnetic zone.
Right, yeah, thank you, Hao, for the introduction and welcome to my talk, the last talk of today's session. It would have also been the last talk at the APS meeting, at this meeting day on Monday afternoon, so it kind of closes the circle here. The work I'm presenting today on backscattering in topological edge states has been carried out in the lab of Professor Ali Mastani at Princeton, mostly together with my co-worker Yang Xie. And yeah, we had a lot of interesting discussions, support also from Andre Bernewick on theoretical questions. Well, generally there is perhaps almost for 2 decades now a lot of interest in topological insulators, which I guess is mostly driven by scientific curiosity about new electronic phases of matter in materials, which have been known for a long time. In fact, what most people are interested in is understanding how a material insulating the bulk can have conducting surface state. For instance, in the case of the 2D topological insulator mercurium telluride, you'll find that the topological bulk gap in 2 dimensions is encircled by 1-dimensional topological edge modes and running around the perimeter. And what's important about this edge mode is that it's protected by the time versus symmetry existing in the bulk, and it means they don't gap out at the gamma point, and also very interestingly, as they basically run around the perimeter, owing to this time versus symmetry, backscattering is forbidden. And this has very important ramifications. For instance, when you look at transport experiments along these 1-dimensional edge states, you'll find that owing to the absence of this backscattering, you'll find a quantized conductance, ballistic transport along these 1D edge states. Absence of backscattering has also been observed in SDM experiments. For instance, what I'm showing here is now a study from our lab about 10 years ago, where quasi-particle scattering between different parts of the band structure of the 2-dimensional topological surface state of bismuth antimony was found to show that backscattering is suppressed. And what I want to talk about today is now our approach of how we can deliberately introduce backscattering into topological edge state by introducing a time versus symmetry breaking phenomena. And the platform we want to use for that is bismuth. It has long been recognized that bismuth 111 bilayers are a topological insulator in 2 dimensions, which is encircled by a topological edge state protected by time versus symmetry shown here. In fact, recently STM experiments in our lab showed that when you look at the surface of a bismuth 111 bar crystal, you'll find localized 1-dimensional edge states existing at the edges of the topmost bilayer. More recent theoretical analysis also discussed the possibility that bismuth is the first example of a higher order topological insulator, and also other people debate whether bismuth could be found somewhere between a strong and weak DI. While this debate may not be settled yet, I think there's still enough convincing experimental evidence existing that bismuth does have a topological edge state. And now we use this topological edge state in combination with local magnetism to introduce backscattering. What you can see here is the surface topography of our sample. What we have been looking at now is not just a bulk crystal, but actually a hybrid structure where we grow bismuth thin films on the surface of niobium. The reason why we do that is because this platform is also very suitable to study the emergence of localized Majorana zero mode in these topological edge states. And if you're interested in that, I would like to refer you to our recent publication on that. In any case, so what we set out now to understand is whether also these thin films do host this 1-dimensional topological edge state, and if so, how it reacts as we combine it with iron clusters, which we have grown in terms of self-assembly at the edges of these bilayer islands. So when we place our SDM tip at the edge of such a bilayer island, we do find that indeed a localized state exists, which peaks at about 180 millivolt. Now as we move our tip away from the island edge onto the surface of bismuth 111, we'll find that this peak disappears, but instead a high energy feature emerges. Now we can also map out the height of this peak, and what we find is kind of consistent with previous studies, such that every other edge shows a very localized one-dimensional edge state. All this matches previous observations, and this gives us good confidence that indeed also the thin films we drew are hosting these topological edge state. And the next step, which I like to discuss here, is how we can confirm the ferromagnetic nature in these nanoclusters. The way we do this is to use spin-polarized STM experiments. What we can do here is to make use of the magneto-tunnel resistance between an STM tip, which is magnetic, and the magnetic sample. What we'll find is that the conductance between aligned tip and sample magnetizations will be higher compared to the case when your tip would be anti-aligned to your sample. And now this gives a measurable effect in a tunnel current, which you can use to characterize the magnetic properties of your sample atomically resolved. When we place our tip again on such an iron cluster, we do indeed find that measurements with tips having opposite spin polarization will give density of states measurements or DIDV measurements, which are strongly different. And from this we can readily calculate quite a strong spin polarization for these iron clusters. As we move our tip now onto the bilayer terrace, we can repeat this measurement as a sort of consistency check, and obviously the spin polarization should go away from these iron clusters. If you're interested in more details about the magnetization characteristics of these clusters, I would like to refer you to our recent paper, because this would be beyond the context of this talk. Now, as the last part of my talk, I would like to discuss what happens as we now study the quasi-particle interference inside these one-dimensional edge-state band structures, and what happens as we decorate them with iron clusters. When we take a so-called spectroscopic line cut along a pristine bismuth bilayer edge shown here, which is about 40 nanometer long, we do find that below the Van Hove singularity of this edge state, a dispersing enriched QPI pattern exists. If we now take the Fourier transform of these data to understand the scattering features, we do find a very pronounced, strong QPI vector, which we call Q1. There's also another vector existing, which is very faint, it's hard to see, it's coming in for higher energies, and this was previously found to originate from scattering in this two-dimensional surface state projected onto this 1D state. But for our purpose here, it can be neglected, as it's also, as you can see, very faint. Now, in comparison, when we decorate this edge state with ferromagnetic clusters, the situation changes. What you can see here now is again a measurement of a spectroscopic line cut along such an edge, again about 40 nanometer long. And as you can already see just from looking at the real space data here, the quasi-particle pattern below the Van Hove singularity is much richer and complex. Indeed, as we calculate the Fourier transform, in addition to the Q1 vector originating from 0 wavelength, another parabolic shaped QPI vector arises, which is centered at finite voltages. And this is also more obvious when you look at the waterfall plot, where you can see that in the decorated case we have this parabola-shaped vector, which here does not exist. Now, to understand these features from a theoretic perspective, it's actually instructive to look at the expected QPI patterns from very simple theoretical considerations. What you see here on the left side is a sketch of the bismuth edge state band structure from time binding calculations. And what I want to discuss now is all possible scattering events. For topological edge state, first and foremost, you will have one Kramers pair of bands, which is singly degenerate. For that reason, if you now look at spin-conserving scattering between branches of your bands which have similar spin, you can only observe one scattering vector on your pristine edge where the spin is conserved, Q1, showing this characteristic. And this exactly matches what we have observed. Now, if spin flip scattering would be allowed, for instance, in the presence of a ferromagnetic cluster, where spin momentum can be transferred, you can have also a second vector shown here in purple. And this would give rise exactly to this parabola-shaped feature, and importantly, this would be centered at finite q. And as you can see already from this very simple consideration, not even with the need of more complex ab initio calculations for the band structure, this one vector to two vector correspondence already tells you quite a bit that what we see here is indeed backscattering induced by time of symmetry breaking from ferromagnetic iron clusters. Now, on the other hand, just to make this a bit more clear, when you look at a trivial edge state, which would have spin-degenerate bands with two set of bands of opposite spin, you would always have two branches for scattering events, because you could always find a spin-conserving scattering for intra and inter-pocket scattering. And so, as I said, this characteristics of having only one vector and then two vectors for the decorated edge state is quite a strong evidence that this is actually the backscattering I was describing. And with this, I'm at the end of my talk, and I want to give you a little bit of an outlook here. What's quite nice now is to discuss the possibility to have a topological edge state in touch with a magnetic iron cluster having a weaker magnetic anisotropy. For instance, one could engineer such clusters having different shapes or even using different elements that may have different properties. And so now one can envision experiments where, for instance, the magnetization of these clusters could be tuned by means of an external magnetic field, or even by means of the spin torque effect from a spin polarized tunnel current from your STM chip into the sample. And this would, for instance, be a quite nice experiment to understand whether it is possible to realize a nanometer-sized magnetic switch that would actually switch between ballistic and resistive transport along these edges. And of course, this would be quite nice and useful for future prospects in the context of spin transport applications. And with this, I'm at the end of my talk, and I would like to thank you for your attention.
Thanks, speaker again, and thank all the speakers in the session.
Yeah, so, well, as the organizer and last speaker, well, it's nice to have the microphone already in my hand. Thanks everyone for being here. Thanks for sitting in late until the afternoon. It's like an APS meeting, right? We start early, and somebody has to be the last guy. That was me. So thanks for bearing with me. And it was great to have people here watching everyone speak, and we saw a lot of great results. Again, not only from physics people, but from people from engineering, from people from chemistry. This was great. And yeah, well, I hope next year we'll have maybe meeting again, and we won't have to do this on site. In the worst case, you know what we do. But yeah, in any case, we'll reach out to all of you guys to have you get your videos, your recordings, and feel free to do whatever you want with them. We encourage you to upload them to the ABS website, to have other people watch them. And yeah, thanks again, and yeah, see you soon.